All right, welcome everyone. I'm Dominic Moritz. I'm a professor at Carnegie Mellon University and also manage the visualization team at Apple. And I'm excited to share this session on the toolboxes of visualization. We have a set of interesting talks. And so without further ado, let's jump into the first talk. So first, Chen Li is going to talk about KMTLabeler, an interactive knowledge-assisted labeling tool for medical text classification. Take it away.
Thank you for the introduction. Okay, I guess we can start it. Hi everyone, I'm Juan, assistant professor from Shanghai Tech University. Today I'll present our work KMTLabeler, an interactive knowledge-assisted labeling tool for medical text classification. This is a joint work with Zhongshan Hospital, Fudan University. Medical text classification is a fundamental task for many clinical studies. It bridges the gap between raw text and healthcare decision-making. Text classification algorithms require large label datasets. However, due to privacy concerns and complexity, label corpora in the medical domain are lacking. Although labeling methods have evolved from rule-based to machine learning techniques like active learning and data programming, their integration in the medical text face unique challenges. First, accurate labeling relies on specialized medical knowledge, but many experts have limited technical skills to use advanced labeling methods. Second, current approaches do not effectively leverage expert knowledge. For example, the same text may be labeled differently based on different research needs, but the current methods lack rapid text task alignment. To address these challenges, we combine machine learning with visual analytics to integrate expert knowledge into the labeling process. In the initial phase, we work closely with experts from a local hospital to summarize the workflow in practice, from which we derive 5 requirements. Following these requirements, we create a knowledge-based model that incorporate domain expertise and integrate it into an interactive labeling tool with knowledge-assist visualization. The core module is the embedding network, which generates contextual document embedding from raw text. However, the initial embeddings are not always suitable for the target task, so the network takes expert input by adjusting the relevance of specific terms and implementing rule-based regulations. In addition, we integrate domain experts' practice into a human ML teaming workflow. For labeling tasks, users first examine significant text patterns. If irrelevant, domain knowledge is applied to align with the target task. For complex samples, fine-grained labeling is also required. Guided by the requirements, we designed the KMTLabeler interface to incorporate the established workflow. In the first step, the control panel enables users to obtain an overview of the datasets and filter instances of interest for labeling. The initial distribution of the selected text is then displayed in the embedding projection view. Specifically, we project the high-dimensional embedding onto a 2D plane using various dimensionality reduction methods to help users select significant visual structures. To identify the optimal cluster numbers, our system employs 3 clustering evaluation metrics. Afterwards, the users can lasso some samples to explore semantic information and validate labels. Detailed information about the samples in the cluster is also displayed in the cluster comparison view. This includes 2 types of information: colored bars for feature comparison across clusters and word frequencies and word weights to capture cluster semantics. If users consider the outcome unsatisfactory, they can customize the projection through the knowledge incorporation process. The weight modification panel enables users to view each text and adjust keyword weights. This panel organizes text based on semantic consistency. To help users adjust word weights, our system uses a blue to red gradient slider to show word weights in the whole sentence. Users can select words and move to the slider to modify weights. However, not every adjustment will generate the desired labels. Therefore, users are allowed to preview the impact of embedding changes on the projection structure. This is done by calculating the semantic distance shown as bar graphs in the embedding projection view, where a higher post-adjustment score indicates better sample separation. To handle complex patterns for various tasks, users can define rules to match corresponding text and adjust the embeddings accordingly. These operations will be recorded in the action record view for checking changes. Once applying the adjustment, the cluster comparison view will help them compare the clustering outcome before and after adjustment by examining 3 clustering groups: auto-automation, colored selection, and the previous automation. To help users monitor dynamic clustering evolution, we propose a customized glyph featuring a pie chart and a stack bar chart for displaying different metrics. Additionally, the label evaluation view helps assess the quality of clustering groups using the clustering evaluation metrics mentioned before. The first 2 steps involves identifying significant patterns to quickly label the data. However, for some samples are difficult to distinguish, instance annotation is necessary. Therefore, we introduce the active learning panel. We adopt SVM as a base classifier and use entropy sampling, implementing the total confidence score to help determine when to stop the labeling process. The up section includes a line plot of confidence scores and a class distribution bar chart for tracking labeling progress, while lower section shows text to be labeled. The system was validated by several studies. We conducted 2 case studies with domain experts for binary or multi-class text classification. However, due to time limits, we will only introduce the first case. So the task involved classifying reports into 2 categories. Before starting, experts identify the dishydrogenation K-class, characterized by compress or inspiration, using their clinical expertise. The cluster number was set to 2 for this task. The experts first selected the initial UMAP projection for its concise structure. They then reviewed the semantic information of the 2 clusters, but find the keywords were unrelated to the labeling task. Moreover, they noticed that the DB index was relatively high, indicating potential issues with the current clustering. To foster improvements, experts reviewed the text in the 2 clusters, finding that cluster C1 have normal class samples, while cluster C2 has a mix of normal and dishydrogenation samples. They observed that the complex was underemphasized and the increase is weighed by shifting the slides to the right. After that, the experts previewed the potential impact on the cluster structure. This preview shows a significant increase in the bar height after the weight changes for C2, indicating a trend towards greater separation within the cluster, which aligns with the experts' expectations. Therefore, they applied the adjustments. The updated results split the previous C1, now C2 into 3 smaller clusters, with 2 belonging to the normal class. However, C.1/ still contains samples with both compressing and not compressing. To adjust this, the experts customized rules, successfully separating the 2 classes and completing the labeling task. We also conduct a user study to evaluate integrating knowledge into the labeling process. So the baseline system is very similar to our system, KMTLabeler, but lacks expert knowledge integration. The results show that our system reduces labeling time and cognitive load while maintaining similar accuracies. Participants also noticed some issues with the learning curve, but emphasized the effectiveness of integrating expert knowledge in accelerating medical text labeling. To conclude, our approach emphasizes a cooperative human ML workflow, which enhances the text labeling workflow by aligning document embedding with the task-specific knowledge through an embedding network, which also integrated into a visual analytics tool. So in the future, we aim to expand our method to multimodal data and leverage large language model for optimization to deeper insights. That's all for my talk. Thank you for your attention, and I'd like to take any questions.
Thanks so much for this presentation. Really, really cool to see how you're optimizing the labeling and showing that it works much, much better in this tool. There's one question on Slido. Can this work be applied to other common text classification scenarios?
Yes, actually, in our paper, we have also discussed the generalization of our approach. So unlike other very common text classification scenarios, medical text require both professional medical expertise and labeling skills. So which require both parties to work closely or lowering the barrier for each party to conduct their work. So our paper chose to lower the barrier for easy and efficient text classification. So in this case, injecting professional medical expertise into the entire labeling process is more emphasized in medical text classification. However, the whole pipeline, including the visual pattern exploration, creating domain expertise, and active learning to label those difficult to distinguish samples, can be easily applied to any other text scenarios.
Awesome. Yeah. Cool. Thank you so much. I have a couple more questions, but I'll ask those on the Discord. So let's move on to the next talk, which is going to be presented by Yves Le Guillou. And it's going to be on TTK is getting MPI ready. Looking forward to hearing that.
Thank you. All right. Thank you for the introduction. I'm Yves Le Guillou. I'm a PhD student under the supervision of Pierre Fortin and Julien Tierny, and I'm here to present to you my paper, TTK is getting MPI ready. My work focuses on topological data analysis. It's an ensemble method that will extract structural characteristics in order to facilitate representation and analysis. In our application, the input is a scalar field on a grid called a triangulation. And this method will enable a user to simplify a structure, identify elements, or segment an image. A lot of those methods are implemented in the Topology Toolkit, an open source software that is available as a C++ library or a PowerView plugin. Our goal is to produce this image. The input is a dataset of 120 billion vertices and was fed into a pipeline, a combination of algorithms that produced this image. Because it is so big, we had to compute the pipeline on a supercomputer, namely Mesu Beta of Sorbonne University. And we computed this pipeline on 1,536 cores, each divided in 64 nodes of 24 cores each. This means that we are in a hybrid multi-process, multi-thread programming, and the multi-process means that each node has its own memory. The memory is distributed, and the multi-process part is implemented using MPI. And this requires quite significant changes to our framework in order for it to work properly. I will now list the different contributions that led us to these results. First, the triangulation. The triangulation is TTK's data structure, and it enables, it allows for efficient query execution and data traversal, and we had to modify it quite a bit in order to allow for the distributed memory context. We also provided examples of distributed algorithm whose performance I'll discuss a bit more later. We provided examples of concrete use cases on massive datasets in order to showcase the proper functioning of our framework. And finally, everything I've just said is implemented and available in TTK. So the first thing I'm going to talk about is the input. So the input is a scalar field on a 2D or 3D grid. And the first thing that we will do is use pair view to divide that big block into smaller blocks with one block for one node. And then we will use pair view again in order to generate a ghost layer. Ghosts are grid elements at the interface of two blocks that we will duplicate on each block because it solves a lot of problems in a distributed memory context. And then we will compute 3 additional data. First, a unique global identifier for each grid element. Second, a process identifier for each grid element so that we know to which process each grid element belongs to. And finally, a list of neighboring processes because those will be the privileged communication partners. Let's talk about the computation steps now. First, everything I've said about the inputs is also true about the output. For example, the unique global unique identifier or ghost generation. This will allow us to use the algorithm in a combinatorial manner. So the first thing that we'll do is execute the distributed preconditioning for TTK with first the ghost layer of ParaView, and then a series of steps that I don't have time to detail here. Then the traditional TTK preconditioning happens, and finally, the algorithm of interest. Again, I don't have time to talk about everything here, but everything is described and explained in our paper. Several algorithms were distributed, and I will now talk about their performance here in the case of a benchmark where the workload increases with the number of cores. The ideal performance is a constant execution time, represented here by an efficiency of 100%. We can divide those algorithms in 3 categories. First, the category of no communication, where all the communication happens during the preconditioning phase. So during the algorithm execution phase, there's no communication left to do. And this leaves us with quite efficient algorithm. The second category is data-independent communication, where we will know beforehand all the communication that needs to be done. And in this specific case, there is an extra cost to that communication. However, once that cost is paid, the scalability is very good. And finally, the last category is data-dependent communication, where here there's no way to know beforehand how much data will be communicated. Therefore, this means that the efficiency will be very likely to vary from one dataset to the next. Let's now talk about real-life use cases, and more specifically, this example. So this image was produced through a pipeline that was fed a dataset of 8.5 billion vertices. The original dataset is very small, and we chose to resample it to this size so that anybody that wants to use our framework can do so, and do so to the best of ability of their machines. In our case, this means 64 nodes. The computation was run on 64 nodes of 24 cores each, totaling 1,536 cores. And the entire computation took 241 seconds to execute. If we look at the more detailed time profiling of the execution, what we can see is that the preconditioning specific to TK in a distributed setting, here in dark blue, red, and orange, is negligible compared to the other algorithm in light blue, and compared to per-view ghost cell generation here in yellow. Let's now circle back to the first example I've shown. So here we have the same pipeline, but a different data set. Here the data set is of 120 billion vertices. Again, we use 64 nodes of 24 cores each for the computation. And the entire run lasted under an hour and a half. Again, we can look at the time profiling of our execution. And we can see again that the preconditioning specific to TDK in a distributed memory context is negligible compared to the other algorithm and compared to per-view ghost cell generation. In conclusion, TDK is now partially usable with MPI with datasets of up to 120 billion vertices. We provided reproducible example so that anybody can reuse our framework. The distributed memory execution introduces an MPI preconditioning, but that preconditioning is, introduces a preconditioning overhead, but that overhead is negligible. The efficiency of our algorithm will depend on each algorithm. More specifically, the algorithm with no communication will be more likely to be efficient than those with data-dependent communication. And finally, all these new algorithms to distribute open new research projects for which we are open to collaborations. Thank you for your time, and I am ready if you have any question.
Fantastic. Thank you. So currently we have no questions on Slido, but I was wondering, you said that you want help. What are some things you want help on? Or I guess work with the community of people to make better?
Well, there are a lot of algorithms within TTK, more than, I would say, dozens and dozens of algorithms. So it's not possible for us to parallelize them all. But now that we have this core framework that works, we think that it's doable for a lot of people to parallelize themselves the algorithms that they use.
All right, so expanding more of the scope of algorithms that are supported. Great. Yeah, it's super cool to see these techniques, and yeah, hopefully we can expand them to really scale up the possible analysis that can be done in visualization. Great. Let's go on to the next talk. And if you have any other questions, please ask them on Discord. All right, for the next talk, Sonia Castelo is going to talk about HuBar, a visual analytics tool to explore human behavior. Take it away.
Hi, can you hear me?
Yes.
Okay, thank you for the introduction. Hi, everybody. My name is Sonia Castelo, and I will present HuBar, a visual analytic tool to explore human behavior based on fNIRS in AR guidance systems. The concept of AR-based task guidance systems is quickly shifting from science fiction to reality. The potential applications of task guidance systems include different domains, such as medicine, mechanic, and cooking. For such systems to be effective, they need to provide useful visual hints that respond to user behavior and mental state. The implementation of these systems typically involve an AR headset, which makes possible to capture data, such as gaze, which track eyes movement to determine where the user is looking, IMU, which captured motion-related data, such as acceleration, orientation, and angular velocity, and may incorporate external sensors to capture additional information, such as fNIRS. I will briefly explain fNIRS a little more, since in our work we use fNIRS to assess the user mental state. fNIRS measure brain activity by tracking changes in blood oxygen levels. We use an fNIRS workload classification model to predict cognitive workloads, covering perception, attention, and memory. These models classified mental state at each time step as underload, optimal, or overload. The challenge begins when we need to handle not only one, but multiple sessions. In summary, the challenges that we encounter analyzing AR guidance systems include the high dimensionality of the data, the nonlinear nature of the task. Unlike linear tasks, where there is only one way to complete a task, in nonlinear tasks, there are multiple ways to finish the task successfully, which makes the analysis of this data more challenging. And finally, finding a way to effectively explore and analyze multiple sessions remains a challenge. The analysis of human behavior using time series data from various sensors, including wearables and AR devices, is well studied. However, these approaches typically focus on single modalities, such as gaze or IMU data, and lack of physiological integration, which are critical for understanding the performer's mental state and how it correlates to their actions. To address this, we propose HuBar, a visual analytic tool for summarizing and comparing task performance sessions in AR, based on performer behavior and cognitive workload using fNIRS, gaze, and IMU data. Our design requirements were defined during a year-long collaboration with researchers and experts, actively developing an AR guidance system to support pre-flight procedures in the context of the DARPA PTG program. The main requirements include performer behavior overview, the ability to align and compare multiple sessions, and detailed visualizations of performer behavior. The HuBar interface is composed of 4 visual components, which allow the user to compare recorded task guidance sessions at varying levels of detail. In the overview, the scatterplot views serve as the starting point for data exploration and allow users to easily identify similar sessions and outliers. Here, each point in the plot represents a session, and different symbols represent either trials or subjects, depending upon user selection. The user can update the scatter plot to represent only the task performer physical activity through IMU and gaze, or brain activity through fNIRS. The workload aggregation view displayed aggregated metrics for performer perception, attention, and memory workload. This view also includes the error contribution, which represents the correlation between the error and the mental state. The event timeline view brings together 4 different streams into a unified time-aligned visualization. Here, session duration is represented along the x-axis. The first horizontal bar represents the procedures performed at each time step. In the error bar, black segments indicate when the performer makes mistakes. In the workload bar, color encodes the performer's mental state, and the line chart represents the model confidence score. Finally, we have the task phase, which may be used to group procedures. This layout allows the user to easily identify errors, note potential correlations, and compare them across different sessions. The experts we interview show great interest in comparing errors, mental state, and procedures, not only across sessions, but also within a session. This is challenging to visualize because the nonlinear nature of the task. We address this in the summary matrix view. It includes a pie chart where radius corresponds to procedure duration and the shade corresponds to the error occurrence. This allows the user to compare procedures within the session horizontally, as well as across different sessions vertically. Users can also hover over each pie chart to see the error contribution plot. Finally, the detailed view includes egocentric video from the performer's perspective. Below this, we use line charts to visualize data from the IMU and gaze sensors, which basically capture the performer's body and eye movement over time. We showcase HuBar using the Ocarina dataset, which was collected by NGC as part of the DARPA program. It contains around 3 terabytes of data from 33 simulated helicopter co-pilot sessions with 7 participants of varying experience levels. In this case study that I will present later, we use HuBar to understand what triggered the underload mental state in co-pilot. But why underload mental state? In the aviation domain, the underload mental state is particularly concerning, as it may indicate that the pilot is overly relaxed or not sufficiently focused. The trainer starts by assessing the data quality using the scatterplot view. Here, in the upper left corner, she identified some outliers. She moved to the event timeline view and see that the trial 19 and 8 have a lot of missing values. Even though trial 20 seems to be comprehensive at first glance, we can see that there is a lot of missing data for workload. She switched her attention to another cluster and moved to the workload aggregation view. Understanding that error may be correlated with mental state, she used the error contribution plot to identify trials where the underload mental state is highly correlated with errors. She identified trial 13 and moved to the event timeline view. Here we can see that there is multiple sessions, very short sessions. Looking at the phase, we can see that all of them have completed just the pre-flight phase, which explained why they are short. Then she focused on the first and last subjects because they are very different. The first one, the pilot have been under the optimal mental state and make few errors. And the last one have been under the underload mental state and make a lot of errors during the sessions. To interpret this, we move to the detailed view. As we can see here using IMU, this pilot has a controlled motion during the whole session. If we compare this with the other pilot, we can see that for IMU signal, we have a lot of peak and valleys, which means that these pilots have been moving the head a lot. Looking at the egocentric video, we can see that the pilot has a manual in front of him, and he is relying a lot on this manual to follow the instructions, which may explain why he is moving the head a lot. To validate our design choices, we interview 5 domain experts. Expert feedback about the interactivity and usability of the tool was overall positive, and they agreed it was effective for detailed behavioral analysis. You can find the complete description in our paper. This work was supported by DARPA. Thank you so much. You can find more information in our GitHub repo, and now I am happy to answer any questions.
Fantastic. Thank you so much. We currently have no questions on Slido, but if you have questions, please ask them on Discord then. I do have some questions. So really cool to see these challenges of high-dimensional nonlinear data and how you address them in your tool. I was wondering why this data in this AR data in particular has this nonlinearity, but other explorations maybe don't, or how maybe this tool could also be useful for non-AR data.
I know it's non-linear because usually when you need to perform a task, you need to follow a sequence of steps, right? It's a linear problem. But it's non-linear because you can solve or you can finish a task in multiple ways. Because, for example, in the aviation domain, a pilot doesn't need to follow the same sequence of steps to take off, right? It can be different. So that is why the sequence of steps can be different. And that is what we called as the nonlinear nature of the task.
Which I guess can also be the case for, like, I don't know, somebody exploring a data set in a Jupyter notebook or writing code. Like there's often multiple ways to do the same thing.
Exactly.
You could have, I guess, so the insights here are applicable more broadly, which is great.
Exactly.
Cool. All right, I have some more questions. I'll ask them on Discord. And we'll go on to the next talk from Jiang, who's going to talk about how does automation shape the process of narrative visualization? And there's a survey of tools here. So take it away.
Okay, hi. So I'm Jiang from Tongji University, and this work is done by my collaborators from Intelligent Big Data Visualization Lab. Our research is influenced by narrative visualization theory and technologies. Previous studies have pointed out that visual data stories require a collection of narrative segments supported by data and presented in a coherent order. And there are existing surveys related to automated visualization techniques and tools. However, none of them have analyzed the different levels of automation in visual storytelling design and creation. Thus, our effort aims to provide an overview of the available design tools and identify future research directions. According to the degree of automation level, we classified the tools into 4 types. The first is a design space, which is a conceptual set of possibilities rather than a real software tools. So design space decomposes design works into multiple design elements, and we can properly arrange and combine these elements according to needs, like the design guidelines. And a second is the authoring tool, which encapsulates key software functionalities and features for the creation. And integrate various menu functions, and users have the absolute control of every detail in such tools. And third is the machine learning or AI-supported tools, which apply intelligent algorithm to facilitate the visualization creation. They usually provide some recommendation solutions in the visualization creation process. However, users still need to manually adjust these recommended contents to achieve the final presentation. And finally, the ML or /AI generator tools is the most intelligent and automatic type. And such tools is designed to reduce the barrier for amateurs who to create visualizations automatically, and ease the burdens for experts to search and select without manually specifying all the visual and narrative elements. And we combine the classification of narrative types from previous research and finally sorted out 6 common types for narrative visualization tools, including annotated charts, infographic, timeline, storyline, data comic, scrolling, slideshow, and data videos. We conclude other emerging genres in the discussion session as well. Based on the 4 types of tools and 6 genres of this narrative visualization, we have summarized 91 tools through this table and identified the key research questions and future opportunities. And next, I will specifically introduce the 6 genres of narrative visualization tools. First, annotation, annotated chart. Annotation is a process of supplementing visualizations with graphics or text, which can help audience quickly understand the chart information. And we clearly have the design space and the authoring tools in annotated charts, such as the chart accent, can provide an interactive interface so users can add annotations manually on the charts. And we have AI-supported tools like Corey to automatically provide annotated suggestions through user interaction. And finally, we have AI-generated tools, which can generate a complete description by recognizing the basic features of these visualizations. And second, we have infographics as a common type of visualization that use graphic elements and icons to illustrate data and contextual information. And in the design, in the authoring tools for informatics, the focus is how to combine images with the data, like the data-driven guides. And for AI-supported tools and AI-generated tools, like the example here, the emphasis is on recognizing the layout of existing infographics and then applying it to the recommended or generated ones. And third is the timeline storyline, which is visualization forms used to describe event sequences. And authoring tools allow users to manually create timelines for some specific scenarios, such as movie narrative, and specific forms, such as matrices and spirals. And AI-supported tools that combine AI algorithm and provide suggestions during the creation process. For example, they can help sort out time text and reduce the time to repeatedly explore the unstructured text document. And the next form is data comics. Data comics can juxtapose multiple visualization information in the form of comic strip. So both AI-supported tools and AI-generated tools integrate the function of data analysis and can visually present the analyzed content and information in the narrative form. The distance between these two examples of supported tools and generated tools is that AI-supported tools require users to manually assemble views to form the narrative data comics. And in contrast, in the AI-generated tools, after user upload the data, it can automatically analyze the data and arrange the data content into a narrative format and directly display it on the page. And then we have storytelling and slideshow. We put these two together as two of these formats. They use this kind of clicking to show the structure layout. And while we have many examples in daily practice of using scrolltelling and slideshow, there's not much research in academia about these automated tools. So we have not as many examples as compared to other genres. And the last type is data video, which combines data visualization with dynamic graphics to tell the story. And authoring tools usually provide existing library of replicable data clips, simplifying the creation of data videos. And AI-supported tools focus on how to recognizing existing static visualization elements and convert them into dynamic ones. And the AI-generated tools can automatically generate data videos directly from the input data. And based on the tools surveyed above, we have compiled such a table where we present how many of the tools in different narrative genres were published in each year. We have also created an online browser tool to facilitate the retrieval of these articles we've surveyed. And by analyzing these tools, we outline the current limitations and future research opportunities at different automation level for narrative visualization. First, at the design space level, for different visualization types, we have different focuses. For example, in annotated chart infographic, its focus is on discussing how to effectively create a correct and aesthetically appealing visualization. And for timeline, data comic, like storytelling, slideshow, and data videos, more focus is on the narrative structure. And compared to design space, authoring tools have greatly reduced the threshold for creating visualizations. However, most of the users targeted by these tools are people with certain level of professional knowledge, like for authoring tools of annotated chart and data comics, mainly requires users to have the data analysis skills, and the authoring tools for infographic and timeline require users to have this visual design skills. And for data videos, user also need to have this video editing skills. And then compared to authoring tools, AI-supported tool pay more attention to the user experience and supports user in certain ways or certain perspective. Like if a designer does not have the analysis skills, they can just use the data analysis function of the AI-supported tool to create like data comics. And we have other types of other genres, narrative genres, which focus on different perspectives. And finally, for tools like AI generator tool, they are easier for users without professional knowledge. Most AI generator tools gain insights into data through automated methods. And in addition, compared to previous tools, this type of tools can directly analyze data and automatically generate the stories with narrative structure and other narrative attributes. And we have concluded the future directions as well. Since our work was published last year, and we have found that some latest studies already involved in the above research directions, like new studies summarize design guidelines for data videos, and for authoring tools, and for AI-supported tools as well. And finally, for the generator tool. Okay, we have been collecting most recent works, and we'll update our web browser as well. If your work falls in any of the categories, please feel free to contact me to add your work into our online collection. And thank you.
Fantastic. Thank you so much for the talk, and also cool to see that there's a tool that people can use. We're out of time, so questions, please ask them on Discord. And we'll go on to the next talk by Alex Ulmer, who's going to talk about a survey on progressive visualization. Pretty interesting design space. Take it away, Alex.
Hello everyone, I'm Alex Ulmer, and today I present our survey on progressive visualization. This work was together with Marco Angelini, Jean-Daniel Fekete, Jörn Kohlhammer and Thorsten May. Let's start with a short motivation for progressive visual analytics. In some cases, visualizations can be provided instantly. For complex use cases, we have to wait until a visualization can be displayed. So how can we bridge this waiting period and gain insights faster? Today, datasets are getting larger and complex algorithms have long computation times. PVA can enhance this process by computing and visualizing partial results, allowing users to gain early insights and steer the progression. PVA requires adaptations on the data processing part as well as the visualization. In this survey, we put a focus on the visualization. The scope of our survey are papers with prototypes of progressive visualizations that were published in peer-reviewed conferences, journals, or workshops. The challenge was finding all related works because the concept of progressive visualizations has different names in other research areas, such as iterative, incremental, or approximate visualization. Overall, we found 96 papers related to PVA, which we tagged with these 5 categories. At the end, we had 48 papers from 1999 to 2023 that were within our scope. Based on the surveyed papers and other taxonomies, we created the following taxonomy for progressive visualizations. The first categorization is according to the visualization type. We have temporal, geospatial, hierarchical, network, multidimensional, and field visualizations. The types are based on the taxonomies by Schneiderman, Keim, and Manzner. The second categorization is data processing type, which highly influences the visualization design. The types are data chunking, process chunking, and custom chunking. While the first two are based on the work by Angelini et al., we added the new variant of custom chunking because some of the surveyed papers presented novel chunking ideas. The next three categories are data domain, visual update pattern, and key properties, which I want to describe more detailed now. First, the data domain, with its two types, known end and unknown end. The known end is more common and means that the full dataset is known or the final result of the algorithm is deterministic. This allows for the upfront definition of value ranges, aggregation levels, and the layout of the visualization. Additionally, the visualization can display a quantitative progress and decreasing uncertainty. The other type is the unknown end and has two variants. Either the dataset and the computation time is unknown, or the final results are not deterministic. In this case, the visualization needs to be adaptive. The layout, visual mappings, or aggregations have to be robust to new values. The takeaway here is that the design of progressive visualizations is highly dependent on the data domain. The next category in our taxonomy is the visual update pattern, with the two types, extension and override. A visualization that is updated by extension adds partial results to the canvas while maintaining prior results. For some visualizations this is easier, like scatter plots, but displaying snapshots of networks quickly fills the display space. The override update pattern can be performed partially or fully. In this case, partial results modify prior results or replace them. The key message here is that the update pattern needs to support the analysis task of the user. Finally, we added 4 key properties for progressive visualizations to our taxonomy. The important note is that they all are very beneficial for progressive approaches, but not mandatory. I will explain that in the following. For example, uncertainty visualization is crucial to show the user that the partial results do not represent the full data. But in case of temporal data with a chronological progression, the partial data is always accurate for the process timeframe. This makes it unnecessary to visualize uncertainty. Visual stability is also important, so that the user is not confused by frequent changes in the visualization. The key is to keep the mental map of the user intact. For progressive visualizations with low update frequency or small visual changes for each update, this does not pose a problem. Interaction and steering is a key feature of progressive systems to give the user the control to process relevant parts of the data first. However, in some systems, the progression may be fixed to an optimal path or has technical constraints, just giving the user the possibility to start and stop the progression. Finally, real-time processing is important to provide fast partial results to the user, especially if multiple progressive functions are chained. But in some cases, this is not feasible because supporting data structures have to be computed before a steerable progression can start. This completes our taxonomy based on our related work survey. You can browse all related works at visualsurvey.net/pva with interactive filtering and additional information on evaluations and application areas for each paper. On visualsurvey.net you can also create your own surveys or literature collections and share them privately or publicly. Our survey uncovered multiple research gaps that are explained in our paper. To conclude this talk, I want to highlight 5 general challenges. First, there are currently no visualization libraries that support progressive approaches out of the box. Although some provide the necessary customization options, they need to be implemented for each visualization. Second, the exploration of progressive visualizations is limited. For example, we have not seen radial progressive visualizations during our survey. The third challenge is the analysis of visual stability. Although being a key property, it is not defined and evaluated sufficiently. The fourth challenge is the progression in multiple dimensions. Currently, almost all approaches progress along one dimension, for example, the time or the topology. The parallel progression in 2 or more dimensions with interactive steering is very challenging. Finally, the evaluation of progressive systems needs to be improved. It is necessary to have metrics that show the benefits of early insights to demonstrate the advantage of progressive visualizations over traditional ones. This was a short introduction to our taxonomy for progressive visualizations. If you are interested in detailed research gaps for each category or new custom chunking ideas, I recommend you to check out our fully stacked 20-page survey paper and the Visual Survey browser. Thank you for your interest in this topic, and I am ready to answer your questions.
Fantastic. Thanks so much for the presentation. Super smooth. We actually have quite a bit of time, so people, please ask questions on Slido and Discord. But I'll kick off with a question, maybe a meta question. But how did you have those captions on your presentation? That was pretty smooth to have those in there.
Yeah, it's
Did
just
you like have to build that by hand, or how did you do this?
yeah, it is 50% by hand, and the other half does the software. It's from Camtasia. They have this new function of automatic captioning. You just have to correct some stuff.
Cool. Please share that in Discord. I'm very curious. Would love to share this with others. Yeah, so super cool to see the gaps that you've identified there. I'm specifically interested in from a tool perspective, right? You said that Visual Progressive, or there's not really many tools that have adopted progressive visualization. And I was wondering whether you, from your literature search, what you found were those gaps. Was it that, or why there are those gaps? Is it because people don't see the value, or is it because it's technically challenging? And if it's the latter, like why exactly?
Yeah, so it's this trade-off. It's technically challenging, and the benefit is sometimes not seen immediately. So you need to have these constraints that you, for example, have large data or slow algorithms, and only then progressive visual analytics can help. And if you're just doing regular size data sets, it's not so beneficial. But then if you have these large data sets and you use these algorithms, it's helping a lot. But the setup is really difficult because, yeah, if you want to visualize something progressively, of course, you have in some libraries update functions, so you can animate some changes in the visualization, but that is really customized work. You have to look at every bar in the bar chart, for example, and move it to the correct place, change the height, change the width and everything. And yeah, it would be really great to have something like out of the box so you can focus on the real problem and not on all its technical details.
Yeah, so I guess building it into tools, I guess it needs to be in the whole stack. So from visualization all the way through like data processing and so on, building it into one of those stacks to make it easy. Yeah, cool. We actually have a question on Slido now. So what in the materials you reviewed can provide reasons for why it may be difficult to implement? Actually, that was my question. So, well, let's see whether. I think that's the same question. So if you disagree, please ask on Discord.
And that's what I can also say. That's what I analyzed a lot was the visual side of the progressive stuff. So implementing the visualization is difficult, but we didn't we touched a little bit in the survey about the data processing part, but that should be another full survey to analyze all the progressive algorithms and how can we produce these intermediate results and also set the frequency in which they are sent to the user. Because if you have a really cool and fast progressive algorithm and it spits out these results in 10 milliseconds, then the user is just overwhelmed with so many updates. And yeah, this also has to be steered.
Yeah, so I guess the user experience matters as well. Yeah, and absolutely. I mean, there's a lot of work in the database community on these progressive and approximate query processing systems. And really also, none of it really has made its way into commercial systems, which is interesting. So there's also, I guess, a lack of actually backends that support these kind of progressive processing.
Yeah, but there are some people here also at the conference that are working on it. We also had a workshop on Monday.
Yep.
That was really great.
Good call, yes. Yeah, there was the whole workshop. That's super interesting. All right. thank you so much.
Thank you.
Then let's go on to the last talk. So John Guerra is going to talk about reusable and reactive widgets for information visualization. So take it away, John.
Perfect. Thank you very much, Dom. Let's see if we can get all of these things working. And do we have slides? So it seems that there we go. Perfect. So I hope everything is on tune. Thank you very much again for the introduction, Dom. And I'm here today to speak about this concept that it's like a new design pattern for actually creating reusable and reactive widgets, which is a perfect segue for the conversation you were just having. And it's how can we maximize the impact of the things that we're creating here in the conference. So the reason why I came up with this idea or started working on this is because there's a lot of great tools that we keep on developing in the community, like things like Lineup or Offset are two specific examples that I wanted to use in my own projects for visualizing COVID data in Colombia and things like that. But when I tried to do that, what I found is that even though many of these things will publish software as open source, it wasn't easy for me to extract just the widget that I wanted. I connected it with another application. And this is even true for other papers and contributions, like, for instance, the grade centered widgets or the double range slider that are quite old right now, but even now they are really hard to use in larger applications. So let me show you with an example from one of my favorite projects that came out of the ACIL in the University of Maryland, which is a space tree. So the whole idea of a space tree is that it's a widget that allows you to select elements in or navigate a large tree. And then they actually publish an open source or rather like a software on Java where you can go and select different parameters, load your own data, and then interact with the widget, right? But what I want is to actually extract just the widget part of that. I want to use that, hopefully go and put it into a modern application, like a new implementation using new technologies, and be able to actually embed it as a reactive widget into, for instance, the US federal budget, and then be able to slice and dice the data in the budget depending on the characteristics, and then be able to select what are the different parts of the budget and see what is the evolution of that over time. So I want it in a larger application, and I wanted that if I have that piece implemented in the tree and something else on Vega Lite or Mosaic or whatever, I can actually combine them. And if I'm even rendering these things on Svelte or something else, like I can actually do it. And that's kind of hard. And if we think as researchers, one of the things that we most commonly do is that if you come up with a new technique, you're supposed to run a control experiment or some sort of other experimentation that compares your contribution with the state of the art. So for instance, in here, I did a little adjustment, just comparing that exact same data that I generated in there with many of the different visualizations or layouts for trees in D3. So, and I was able to do this because I am actually looking at them and implementing them as different reactive widgets. So that is the concept, and actually, let me tell you a little bit of the inspiration. Where does this come from? So it all starts with web standards, like modern web standards. If you go and create any application right now on the web, you're probably going to be using some inputs, like for instance, a text input here from the MDM documentation, and that input, you can select it with JavaScript. And if you want to get the value for that input, you just look for the dot value attribute, and it will generate input events. So this is nice, and it's standard in general. You can use it in other applications, like for instance, the folks from Observable in their notebooks, they created this very nice library of inputs that were like enhanced inputs where you actually could access the reactive value of the input and then reuse that in the notebook and get magical, almost magical interactions between things. So when I saw those, I started using them extensively and creating my own. And then I started saying, well, I want that, but I want it also for visualizations. Like I love interactive visualizations, and I want that if I have an interactive visualization, be that the input that I'm using for some other visualizations or for connecting it in other examples. And that's how like that came to be. And the whole idea is that since we are using standards in here, it doesn't really matter if you do it in Observable or outside. So therefore, I'm introducing here this concept that I think could greatly benefit the community, is that if we all can start using this type of design pattern, then we can distribute our contributions more easily. And let me show you how easy it is to do it. So the only thing you need to do is to put your visualization and then embed it or wrap it in a function that takes as parameter first your data, of course. I recommend tidy format, and then some parameters or options for that. And this is supposed to output an HTML element, an HTML view that you can actually then render using whatever framework you're using. And that one, following the idea of the inputs, just have a value attribute that in this case is going to contain whatever dynamic or reactive attribute or parameter you want in your visualization. It could be, for instance, the current selection. And then in order for it to be reactive, you just need to dispatch input events whenever the value changes. And if you want to get fancy, you can also listen to input changes that will trigger like re-renderings inside your widget. If you want to get hardcore, let's go and take a look at that in code. So if you have a basic D3 implementation, like for instance, like just showing some circles in there, again, just wrap it into a function. That function takes some input data and option parameters that of course you use for your visualization. And then the idea is that you return your HTML element. Please notice that in this case, we are not asking D3 to do the rendering. We're just telling D3, please create a DOM virtual element that then I can go and render using React or Svelte or whatever. So let's simplify the D3 part. And then remember, the next step will be just to add the value attributes in here. And we are also going to have a show value function that updates if the circle is selected or not, painting it red. And the idea is that when the user clicks on the circle, then they can actually change the color using the show value and then dispatch an input event, which is going to trigger the reactiveness. Now, again, going into the fancy part, you can put getters and setters for the value attribute and then listen for the input event. Now, if all of this seems too complicated and too much, I'm here for you. So I created a helper function that I published just a bit ago as a NPM package that you just need to add one line of code to wrap your HTML element, and then you provide your show value function, and you are also going to get this convenient set value function that you can use for whatever interaction you want to trigger the reactiveness. And if you're like me and you're in love with Vega and Vega Lite, and that's kind of your tool of choice for most of your visualizations, then I'm also here for you. I also created another helper function that I call Vega Selected that basically based on any Vega or Vega Lite JSON specification, you can just wrap that specification and convert that interactive visualization into a reactive widget. So it's just one line of code, just provide that. Here is an example with the great Vega Lite JavaScript API, creating a brushable scatter plot. And as you can see, it converts that into a reactive widget that I can use as an input in a larger application. So if you want to use these widgets, how do you combine them? The idea is to be able to create like larger applications that are all highly connected. So I already showed you an example with the space tree demo. And then the idea is that I have another widget that contains a timeline. And then every time the value on the space tree changes, the selection changes, I take the value of that and I connect that with the input of the timeline. And that shows the example that I was showing you before. And then the cool thing about this is just by doing that, we have another widget on the top, like the reactiveness takes care of all of that. Now, what if you want to create something more complex? Like you can go and even combine things like a Vega Lite scatter plot that we had before with a D3 histogram. And since this is a widget, we can also have it vertical. And then same idea. We just take the value of the selection of the scatter plot and we use it as the input, but in this case of the options or the current selection of the scatter plot or the histograms. And then to connect it back, you can just listen to the changes of the input value. And by doing that, you can create a simple application like this, where you have a nice synchronized view where you can select and brush on the scatter plot and have those changes reflected in the histograms and do it backwards as well. And everything nicely connected and reactiveness is taking care of all of that. So let me show you a larger example. In this case, using the Yuma Playground, which is an application that I created where you have like a widget where you can load your own data and then add that as a widget, then that is going to give you the original data that you can show and visualize using an Avio widget that allows you to filter the data. I pass that to a web worker UMAP widget that is actually running in the background and is not even rendered, but allows you to convert your high-dimensional data into 2 dimensions that then you can show with your brushable scatter plot, and using visualization, mantra, and the details on demand, you can show whatever is selected in a table. Now, since we are using these black boxes, then you probably want to select what attributes you want to include in the dimensional reduction and what are the hyperparameters of your UMAP algorithm and even the parameters of your brushable scatter plot, so you can show like how it is changing for different variables and things like that. Now, showing this because of that, I had that application and I had all the widgets, I was able to build the IEEE VIS paper explorer that I actually built during the last year's conference. During the conference, I was able to create the first prototype, which speaks pretty poorly about my capacity for paying attention in the conferences, but very greatly about this new design pattern that I'm just introducing today. So with that, I will invite you all to go to johnguerra.co/reactive widgets and let me know what you think. And let's consider using this because it could be great for our community. And with that, thank you very much for your attention. Special kudos for Dom and all the team of Vega and Vega Lite for their great contributions, D3, Observable, and the great Druid.js library that allowed to build many of these things. And with that, let's hear if we have any questions. Thank you very much.
Awesome. Thank you so much. Super exciting to see how we can really use like web standards as part of this kind of proposal for an API, and how it's already interoperable with many existing tools out there like React, observable notebooks and so on. Question from Jean-Daniel. What if your example has, or what if there's a cycle between inputs and outputs between components?
Oh, that's a great question. So thank you very much for asking that. So 2 things. Like the first is that you can actually use this outside of Observable pretty easily. It's just like you have to write a little bit more of code. And then since you can control that, then you can also do things like binding widgets. So the nice thing about this is that you just create like a hierarchy between your widgets. And then you say you're going to have one widget that is going to be like the main controller. And then the other one is going to be the one that follows the lead. So in that sense, you can update the secondary one based on the first parameter, like as I said before. And when you send the message back, you just make sure not to dispatch the input event, and then you create that. If you're doing that inside of Observable, it's actually quite easy just to do with this inputs bind that they have in there. But if you want to do it outside, I just did a demo yesterday, and it's just that idea. So it's just like make one primary, the other one secondary, and then change the value from the secondary to the input. So it might make more sense to share some code with you. But thank you very much, Daniel.
Yeah, I think I want to see that as well. So for instance, what if you have multiple histograms and you want to do cross-filtering between them, where you want to filter the other charts by the brush in one chart? How would that work?
So I think one of the ways that you can make that one work, like once you start working with this, you start coming up with strategies, like tips. Like one of the ones you can do is that you can create like a source of truth that is going to be kind of like your main widget. And you don't even render that as anything. And then you use the other ones as the secondary ones, right? And then each one of the secondary can trigger events that are going to update the source of truth, but this is the one that is going to keep the changes. So I think I have done that, and if I'm not mistaken, I did it in the Paper Explorer, where you can actually, let me see if I can run to that quickly. I mean, it's not showing the code in there, but at the least, I think at least it has some of that in the sense that you have like those selections in here, and I can filter by like the different areas. You can change and have the dimensional reduction be recomputing. But then, of course, you can also come into these extra options. And then I have like a faceted select search in here. You can search for different authors. You can go and say, I only want to have these ones. And then again, since you have like a main source of truth, then that's the one that is controlling and it's avoiding having these loops.
I see. So yeah, having one kind of drive. So you basically, instead of having cycles, you have a DAG. Okay.
Yes.
Cool. Awesome. Obviously, there's lots of questions about scalability and so on that it's like one of the authors of Mosaic I'm very interested in. So, but let's take those offline. Thanks so much, everyone, for coming to the session. Thanks so much for Chen, for Leah, for Sonia, Ching, Alex, and John for presenting in the session on the toolbox of visualization. And yeah, looking forward to all the cool work that's going to be built on top of this. So thank you so much. Again, I'm Dominic, and look forward to the rest of the conference. Bye-bye.
And thank you very much, Dom, for organizing.
Happy to.